Hey guys, sorry for the lateness of this video. Hopefully it will be posted by this afternoon and you guys can watch it before tomorrow. So we are going to finish talking about acids and bases. The last discussion we had to have was about pH. Now if you're following along with your slides, you should see the slide on the pH scale. Now I'll show you what I've got in front of me so that you can see it. Well, you can probably see it on the board here, or you can see it on my little computer right there. Alright, so what we're going to talk about is pH and the pH scale. Now, pH is a measurement somehow of acidity. pH scale is a scale from 0 to 14. Now, when we think about pH, we think about a couple of different ways that we can test acidity of some solution. Now, we can use things like a pH probe, a pH meter that will tell us an exact pH. We can use pH test strips that can tell us the general pH by comparing to some pH guide. We can also use something called litmus paper, which will tell us just generally if a solution is considered acidic or basic. Now, when we think about pH, we think pH has to be a measurement of acidity. So what exactly do we measure in a solution to measure acidity? Well, we need to measure concentration of H3O+. We should be remembering that H3O+ is what comes about when I add acid to water. I form H3O+. So when I think of pH, I actually think of measuring the concentration somehow of H3O+. pH, the big equation here is pH equals negative log of the concentration of H3O+. Now I can write this a different way. pH is equal to negative log of the concentration of H+. Now we should remember that in a solution we actually don't find H+. We don't really see it in there. What we see is that this H+ combines with water to form H3O+. So what we really think is we can measure the concentration of H3O+, while H+, we say again, does not really exist in solution. We have that combined with water to form H3O+. Now, when we're thinking about these solutions, we should be thinking, well, how does this pH value tell me about the acidity of my solution? So let's try a couple of examples. If we look at concentration of H3O+ equals 0.1 molarity versus some solution that has a concentration of H3O+ equal to 0.01 molarity. We should be thinking, okay, so I've got more H3O+ in this top solution than I have in the bottom solution, meaning my top solution, if it has more H3O+, that means that I must have added more acid to produce more H3O+. With that in mind, then, I would think that this solution is more acidic. I had to add, again, more acid to produce more H3O+. This solution down here must be less acidic. I must have added less acid to produce less H3O+. So, with that in mind now, if I'm going to calculate the pH of these solutions and see what this pH tells me, again, I'm going to take pH equals negative log of the concentration of H3O+. Here I have negative log of 0.1. For my next solution, pH is equal to negative log of 0.01. If you take out your calculator, my handy-dandy little calculator right here, you should see a button that says log. So if you look on your calculators, you should see a button that says log. So when I'm calculating this, I will just plug in negative log of 0.1 and I should get a pH of 1. Now, units for pH. Confusing, confusing? There are none. There are no units for pH, so I would say that for a concentration of 0.1 molarity, my more acidic solution, pH equals 1. Now let's try it for the next one. My next one, negative log of the concentration where it is 0.01, and I get a pH of 2. pH of 2. What you should be thinking now is, well, looking at my solutions, as my concentration of H3O+ goes up, again, that means I've got a more acidic solution. As my solution becomes more acidic, my pH actually seems to be going down. So when I think about my pH scale measured on a 0 to 14 scale, I should be thinking, well, lower pH must correspond to more acidic solutions, while higher pH corresponds to more basic solutions. So when we're thinking about pH, a lot of times we think of acidic, we think of basic, and then we think of right smack dab in the center, we think of a pH right in between. Now this pH can't possibly be acidic, it can't be basic, so it must be neutral. Now when we think of neutral, again, we should be thinking of things like water and salt. We should remember this a little bit. We think of water and salt. So now, when I have some kind of equation, in this case I was given solutions where I know the concentration of H3O+, but what if I'm given the pH of a solution, some number, I'll call it maybe 4.5, and I want to know, well, what is my concentration of H3O+? So what we use is one more equation, which we say is actually the inverse of this equation here. pH is equal to negative log of concentration of H3O+, while concentration of H3O+ is equal to 10 to the negative pH. Now we should remember, pH does not have any units, but concentration absolutely does. So if I'm going to solve this equation here, I have pH equals 4.5, my concentration of H3O+, I would say, is equal to 10 to the negative 4.5. Now I take out my little calculator here, 10 to the negative 4.5, and I end up with a concentration of H3O+ equal to 3.16. In this case, I'll go with 3.2. 3.2 times 10 to the negative 1, 2, 3, 4, 5. And again, there are no units on pH, but there are definitely units on concentration. Units should be something like moles per liter or molarity. So my concentration of H3O+ would be in units of molarity. Alright, so that's pH. Now, sig fig rules are written at the bottom of that slide. You should be able to see the sig fig rules, but again, I am not too concerned about sig figs. Be reasonable with your numbers. Again, all I ask is for you to be reasonable for pH calculations with your sig figs. Now, trying a couple of the problems, you should see a couple of problems, and I actually added an extra one for you. So, the first problem up there asked us, what would be the pH of a 0.1 molarity H+ solution? So I've got H+ concentration equal to 0.1 molarity. Hopefully you guys can still see this. And I'm looking for the pH. pH, again, is equal to negative log of the concentration of H3O+, also known as H+. Again, we can consider that to be the same thing. So my pH is equal to negative log of 0.1. When I find my pH is equal to 1. Next question asks, well, if I have a solution, some solution, and the pH is 3. If the pH is 3, pH equals 3, what is my concentration of H+? Now again, we should not be concerned with the fact that we're writing H+, rather than H3O+. We can consider them to be the same because we remember H+, when it is released or donated by an acid, we know that it instantly comes into contact with water to produce H3O+. So again, I should be thinking that every time I see H+, I'm also thinking of H3O+. They can be in our heads. We can think of them as synonymous. So now, H+ concentration or H3O+ concentration, my two equations here, I have H+ or H3O+ concentration is equal to 10 to the negative pH. In this case, I have negative 3. So my concentration of H+, I would say, is equal to 1 times 10 to the negative third. Always remember, pH doesn't have units, but molarity are my units for concentration. Now, the last question, hopefully you guys pause the video to try to work on it yourself. But the last question asks, if I put 3.5 grams of hydrochloric acid in 50 milliliters of water, what is the pH of the solution? So now we should remember, I'm going to erase this for a second and we're going to write it down somewhere else. pH, I should remember. pH is equal to negative log of the concentration of H3O+. The problem says that I have 3.5 grams of HCl, and I put it in 50 milliliters of water, H2O. Okay, now thinking about this, 3.5 grams of HCl and then 50 milliliters of water, can I solve for the pH with these numbers right away? I don't think so. I need to know the concentration of H3O plus to find pH, and my concentration of H3O plus is going to be equal to moles of H3O plus per liters of my solution. Now, I have milliliters of solution, so might as well start there. My 50.0 milliliters of solution, or water in this case, for every 1,000 milliliters, I have 1 liter of solution, so I end up with 0.0500, liters of solution. So, my concentration of H3O plus, I can now solve at least for my liters. I have 0.0500 liters and question mark on moles. Now you should be thinking, well, I've got grams of hydrochloric acid. I must be able to get to moles, so might as well. 3.5 grams of HCl. To go from mass to moles, I should be thinking molar mass. I have about 36.45-ish grams of hydrochloric acid for every 1 mole of hydrochloric acid. I end up with, well, let's look, my handy-dandy calculator, 3.5 divided by 36.45, and I end up with 0.096 moles of hydrochloric acid. Now, we should be thinking right at this second, I've got moles of hydrochloric acid, liters of solution. I can find molarity, but I can find molarity of, well, hydrochloric acid here. Hydrochloric acid is not the same as H3O+. But what do we know that hydrochloric acid will do in a solution of water? We should be thinking hydrochloric acid, that many moles of hydrochloric acid in water. We know any acid in water will produce, hopefully you've guessed it, H3O+. And again, I'll have my Cl-, but he's not all that important right now. So, I look at my reaction. What is my ratio of hydrochloric acid to H3O+? Should be 1 to 1. So looking at this now, I have 0.096 moles of hydrochloric acid, and I have a reaction that tells me a ratio between hydrochloric acid and H3O+. So I should be able to convert using my 1-to-1 ratio, 1 mole of hydrochloric acid for every 1 mole of H3O+. I find out that I have actually now 0.096 moles of H3O+. I can take that moles of H3O+, put it up here, 0.096 moles of H3O+ to find some concentration. I'll find my concentration of H3O+. My concentration of H3O+ now is equal to 1.9 molarity. I find my concentration of H3O+, and finally I can find my pH of the solution. All I have to do is plug this number right into here. Now, pH, negative log of my 1.9, okay? I get something like negative 0.28. And again, pH has no units, but a negative 0, how is it possible to have a negative pH? That sounds like crazy talk. What you should be thinking is, I've got a lot, 1.9 moles per liter. I put 3.5 grams of acid in only 50 milliliters of water. That's a lot of acid. What would you say about this solution? Would you think it is basic, acidic, or neutral? Up to you now to think. That negative value, hugely, hugely acidic, right about there on my scale, incredibly acidic. Now, the last thing we're going to talk a little bit about is the pOH scale. The pOH scale. When we think of pH, pH stood for power of hydrogen. pOH, on the other hand, is another similar scale, except this time pOH is equal to negative log of the concentration of hydroxide. pOH is power of hydroxide. So now, I look at these equations that I have here. I'll kind of box them on the side. Hopefully you guys can see up here. pH is equal to negative log of my concentration of H3O plus, power of hydrogen. Concentration of H3O plus is equal to 10 to the negative pH. POH now is equal to negative log of my concentration of hydroxide. And remind yourself, where does hydroxide come from? Well, H3O plus comes from acid in water. Hydroxide comes from base in water. So POH equals negative log of hydroxide. And when I'm looking to solve for concentration of hydroxide, I should remember that, well, up here I was able to take 10 to the negative pH to solve for H3O plus. I should now be able to take 10 to the negative POH to solve for concentration of hydroxide. So those are 4 equations that we are definitely going to need to know. Now, pH and POH are actually related. We should remember that my Kw, whatever that value was equal to 1.0 times 10 to the negative 14th, which is also equal to, I'll write this, Kw, equal to my concentration of hydroxide times my concentration of H3O plus. And I'll erase some of this so we get it out of the way. Now, my concentration of hydroxide and my concentration of hydronium are related, which means that pH and POH must also be related, and they are related by this fancy number 14 that we keep seeing. So all of these relationships we have give us some idea of, well, if I know a concentration of H3O plus, I can also know my pH, I can know my POH using this equation right here. I can also know my concentration of hydroxide. So given any of these numbers, whether it is H3O plus concentration, hydroxide concentration, pH, POH, I can find any of the other information. Now, a couple of questions that are asked on the next slide. What would be the POH? What would be the POH of a solution, a 0.005 molarity H plus, or I'm going to write it as H3O plus solution? So I've got my concentration of H3O plus. I've got my concentration of H3O plus. Now, what I can do from here is I can solve for my pH. pH is equal to negative log of my concentration of H3O plus. If I solve there, I have negative log of 0.005, 0.005 molarity, and I end up with a pH of 2.3. I end up with a pH of 2.3. Is that the same as my POH? Well, no. We should be thinking, this pH, acidic solution now, how do I solve for my POH? Is there a relationship now between pH and POH? Well, right here, 14. So POH now is going to be 14 minus my pH. And if I have my pH, my POH is then 14 minus my 2.3. So 14 minus my 2.3, and I get 11.7 as my POH. Just like pH had no units, POH also has no units. So the next one, I'm going to have you guys try on your own the 0.426 moles of sodium hydroxide in 1 liter of water. You guys can come talk to me during office hours if you would like to get clarification on it. Now, to end our discussion on acids and bases, what we should be thinking about is, well, why does this impact my environment? And we should remember, the whole topic of this chapter was ocean acidification and acid rain. We think of ocean acidification, and we must first think about the ocean itself and what we have in our ocean. Now, when we think about the chemicals that we have in our ocean, we think about pH and acidity in terms of 3 main players. We think of the carbonate ion, we think of the bicarbonate ion, and we think of carbonic acid. Now, when we think about this, we hear a lot of carbon stuff going on, bicarbonate, carbonic acid. A lot of that is derived from CO2, carbon dioxide. So when we think about our ocean pH, a lot of what we put out into our air is actually getting back into our ocean. We talked a little bit about water and solubility of gases in one of my previous videos, and we talked about how gases can actually dissolve in water. When we think about CO2, we definitely have CO2 dissolved in our water. We can think about ocean acidification as a big process. We think, and I'll show you guys on my screen what I've got so that you can see it as well. I'm sure you have the slides in front of you, but so you can see it as well. We're on this slide here. When we think of ocean acidification, we think of carbon dioxide. When carbon dioxide gets dissolved in the water, what we actually end up with is, HCO3 minus. We should be recognizing this as bicarbonate ion, and we get H3O plus somehow. Now, through a long, drawn-out process, what we actually end up with is carbonic acid. We end up with carbonic acid, and in the end of this whole process, again, we have acid being formed in water, and what we end up with is some substance that is easily or more easily able to dissolve things in water. We think of acid as being burning, corrosive things, and acid in our ocean is no different. So marine animals use this carbonate ion that we have. Now, this bicarbonate ion, again, can further react to form carbonate ions, and when we have this carbonate ion that forms, and again, carbonate, the difference here is CO3, 2 minus. Lots of marine animals use that carbonate ion, and a lot of the animals that we see actually use it in their skeleton. Many of them find it in their homes. You think of shellfish, you think of things that, house themselves in little shells. Shells a lot of times are made of calcium carbonate, again, using that carbonate ion. When we are using the CO3, this carbonate ion, what we end up doing is we end up dissolving more and more of these skeletons, more and more of these shells that contain carbonate ions. And again, acids, eating away at things should be pretty normal to us. We think of acids eating away at things, and what we are doing is actually eating away at these little critters' homes. Kind of sad to think about, but again, this is exactly what's happening. Now, carbonic acid, again, is a big player in our ocean, and when we think about this, it is also happening in our rain. We have rainwater, right? And so the CO2 in our atmosphere is easily able to leach into our rainwater. So when we look at rain, we think of water instantly, but when we think of water, we think of neutral, but in actuality, when we think of rain, we should be thinking of a lower pH, a more acidic pH of rain, because we have that carbonate and the carbon dioxide stuff that's forming acid in our water. All right, now when we think about the average pH of rain across our country, you can kind of see this cool picture that we have, and I'll show it to you again on my screen so that you can see it. We've got this cool little picture, and we think, well, why is there a big difference? Why is there a big difference? In some parts of the country, the pH of rain is actually even lower than 5.3. The most acidic rain actually falls, if you saw in that picture, kind of to the right of our map, of the U.S. map. And the reason for this is because those are really industrialized parts of our country. Now, we think more industrialized, we think more CO2 being produced. We also have more sulfur compounds being produced. We also have more nitrogen compounds because, again, when we combust things, we should remember Throwback Thursday all the way to Chapter 1. When we think about our pollutants, we think of nitrogen oxides, sulfur oxides, and a lot of those things end up resulting in the process of producing sulfuric acid, nitric acid, which gets into our rain and acidifies our rain. If you look at some of the pictures that I've got on here, kind of go through again, we kind of throw back all the way to our sulfur oxides and nitrogen oxides. Now, when we think about the acid rain, there's a pretty dramatic picture of let's see, the marble statues. Marble statues, hopefully you can see it. Marble statues actually get disintegrated by acid rain. The acid is eating away, just like in the ocean we have an eating away of the skeletal structures and shells on marine life. This acid eats away at marble statues. Kind of interesting. All right, so we will finish this off a little bit on our next class, and hopefully you guys all have a great time watching this. See ya!